Well, good afternoon. Thank you very much, everybody. So I'm Newnham. I'm with me, and I'm going to tell you a little bit about the work that we're doing, some of the interesting things some of the interesting challenges we have, and a little bit from my experience going back now 20 years working in this sort of area. So Leomard is my third startup, and I've tried a lot of things over the years. Some of them work, some of them don't. I'm going to describe the sort of approach we take at Leomard and how we got there. So first of all, this is what I'm going to cover. A few words on who Leomard is, and talk about what we do, what our problems are, the problem we solve, and I'll talk about data, about predictive models, about real-time bidding, a little bit about future research, and something about the lessons learned. Just a little bit at the end about the lessons learned over the last few years at Leomard, but also previous companies in the areas. Okay, so who's Leomard? Well, we're the world's largest mobile video platform, reaching over 1 billion users worldwide. And as you can see, it's all about people on mobile devices. We're based in Ukraine and in London, and we're very much a distributed company between the two centres. And the bottom thing is that machine learning is at the core of everything we do. So I'm the chief data scientist. I would say that, of course, but it's extremely important that everything we do has good theoretical basis and that there's proper machine learning principles at the bottom. So the simple diagram of what we do is there's somebody on a mobile device, and when room for some sort of ad, for us mainly video ads, pop up, then a request will go from the phone to a supply-side platform, usually a real-time bidding exchange, and then in real time, many demand-side platforms will accept that request, decide whether to bid for the opportunity of displaying an advertisement to this particular person. So we have a real-time auction happening here, and Leomard and other companies are making bids in real time for the privilege of serving that ad. So that's the simple view. There's a little bit more detail on this diagram. This is not our architecture as such, but it shows all the important parts. So there's just a little bit more detail here. So we've got the supply-side platform at the top. This is where the request comes from via an ad exchange, and then here is the link coming to the DSP. We'll be listening, and we'll go and identify people with an advertiser ID or a device ID, and whatever information we can retrieve, then essentially that goes into what amounts to a bidding engine. We decide if we wish to serve an ad to that person, and if we do, how much we're prepared to bid. If we win the auction, then we serve the ad. Okay, so where do we get the ads from? We have contracts with advertisers, so we have contracts with many big advertisers. So, for example, a large automotive company may be wishing to promote their latest car, and they might come to us, and this is typically what they'll specify. So they'll say they want a certain number of impressions over a certain time period. There's a whole lot of other restrictions that may or may not exist, like which countries and which apps they can be served to. But at the bottom, importantly, then there's a goal. CPM, CPC, CPI might be something else. How are they going to pay us? So CPM is cost per meal. That is, they don't mind who we serve it to. They will pay us for every 1,000 apps that we serve. With CPC, cost per click, then we only get paid if we serve an ad to somebody who clicks on it. Okay, suddenly more important who we serve it to. And CPI, cost per install, we only get paid if somebody installs an app of the after viewing the ad. So, here's a typical example. This is an ad for Nivea skin cream, and we may be asked to serve 10,000 impressions per day for 28 days. So, okay, so that's the environment we're operating in. Okay? So, where we're operating, we're dealing with thousands or tens of thousands of requests per second, and we have to respond within milliseconds. So, when a request comes to us, we have to determine what ads or videos we can show to this particular person right now. We have to score these against whatever KPI we're trying to optimize. So if it's CPC, we have to estimate the probability of them clicking on this ad. We can then simply determine whether we respond or not. Is this person a good prospect? If not, forget it. Let somebody else serve an ad. If not, if they are good, then we have to go into our bidders and determine how much we're prepared to pay. And then lastly, respond. So typically, end to end, we need to do all this in less than 40 milliseconds. Or rather, the 99th percentile should be less than 40 milliseconds, which means that most requests need to be considerably less than that. So this is quite a tough ask. Okay, so that's the environment, that's the problem we're solving. How do we do this? Well, we're collecting data. Without data, we can't predict what anybody's going to do. Then we build predictive models, and then on top of that, we have various bidding models. So I'm going to go through each of those in a little bit of detail. So, first of all, data. So, there's a number of things that we can get. We don't always get all these things, but from most requests, we'll get some sort of user ID, maybe a device ID. We may well get a city and a country and something about the device itself. And there's a few other things that we can get fairly easily. But this is not very exciting data. There's really not a lot there to determine whether somebody is likely to click, or likely to install the app, or likely to do anything. There are some predictive things, but it's not the ideal sort of data. So what we have to do is to augment this data. So one important thing I should say here, before we go any further into this, is that whatever data we collect, there are certain restrictions on what we can collect and what we can't collect. People can opt out of any sort of data collection. Of course, we abide by all the necessary legal requirements. So, after we've taken out, all the things we can't collect and we can't store, then what we're left with is a relatively small amount. So, what we've got to do is a lot of processing of that data to make what we have useful. So, the first thing that we can do is to try and build segments on the information that we have, so we can translate those individual data points into what people actually look like. So, we create many segments, but here's just some things that might be desirable to know. We might, it's very useful to know the age range of people. It's useful to know if they're up to the fitness span, for example. Can you categorize them in some way? So we use three mechanisms in order to build this. So first of all, simple rules. We're collecting all this data against a device ID, and we know what the name of the app is that a particular request has come from. So if you're on an app on your phone and an ad request pops up, then the name of that app is generally come to us. So we might start to be able to build a history of what apps you have on your phone. And so we might then create a simple rule, if, then. Okay? Well, that's all right, but it's a bit crude, and it's very easy to make bad rules. Another thing we do is we process the data and build predictive models. So you can take this data, shove it into a model building engine, and maybe come out with a prediction of their gender. Recently, we've done some work predicting gender from mainly from the apps on the phone, and we were quite successful. So, having a predictive model allows us to move from knowing about 5% of our user base, knowing whether they're male or female, up to getting a reasonable identification on about 30%. But everybody we can provide a score for. So that's a big step forward. The other place, of course, where data comes from is third-party data sourcing. There's lots of people out there who want to sell data, and some of it's good, some of it's bad, some of it's expensive, some of it's free. For us, the question is it going to add any predictive value? And some of these things are free sources which we can build. So, key point here is that we put a lot of effort into augmenting the data. Another way we can do this is location. Sometimes we will get location information. Frequently we'll get IP address. IP address is a questionable usefulness sometimes. So when I look at my IP address at home, it tells me I'm living in a city 50 kilometers away. And I'm not. But the trick is here is to combine it with other information if we have it. We may have Wi-Fi now. We don't usually, but we may do. And if it's a university, it's making a recognizable map. Sometimes we get GPS coordinates. Sometimes those are accurate, sometimes they're not. But putting these three together in a clever way, then we can start to create some useful features from it. So none of these things are trivial, but you can glean information from the data. So the other big area is the creatives and the app itself. So apps are all categorized in various places, and we can categorize users based upon the apps that we see to use. But also the ads themselves, the creatives that we send, then we'll have things like age rating, whether the user has to interact with them, whether there's any audio, and the type of content, whether it's video or a banner ad or whatever else. So we have information about that. So, putting all that together, then this is not, I think I'm finding it hard to read here, so you won't be able to read the detail, but here's an example profile that you can put together from an individual. So here's a profile ID, and here's a bunch of things that we know about them. There's a list of installed apps on their machine. There's a bunch of keywords that they use in some app or other. We've also got here a location history as well. So we can build up a picture of where we've seen these people. And a whole load of other things. So the last thing on data, data continues to grow. This is just a shot from, I think, in the beginning of May. Here's our total number of profiles going from 1.4 billion to over 1.5 billion. We have a lot of profiles. A lot of them, of course, are old and stale and just clogging up our system. But we don't know that until those users don't come back. But one of the problems we have is that data, there's a lot of profiles. We're serving ads all over the world, 1 billion profiles is not a small number. So it's just a list of some of the segments that we're trying to create. Okay, so that was data and about the sort of approach we have to it. It's extremely important to augment that data as much as we can. A lot of data, we need to build some sort of predictive model. We want to predict, is this person going to click, are they going to install, what are they going to do? So, when we build a model, we need to think about the problem we're trying to solve. So, we're trying to match individual advertising campaigns to individual people. So, here's a nice, simple, stereotypical example. Here's a skin cream, and we are trying to match it to people who are likely to respond to that ad. We find for some ads, like skin cream, that we do see these sort of direct relationships, but for many ads it's much more complicated. But the key thing here is we're matching individual campaigns, individual advertising campaigns, to individual people. So, as it says at the top, of course, it's not always this easy. There's many dozens of factors involved, not just sort of skin cream ads to women and computer games to men. No, there's a lot of factors involved. So, the key point here is that we need to model interactions in the data. We need to be able to learn that campaign A appeals to this type of person type X, and campaign B appeals to person type Y. This is the core problem I've been working with for 20 years in other companies as well as this, as well as with me. there are several ways that we can solve it. So the first and simplest method is, a single, simple model. So, for example, logistic regression, we can take all our data, we can take all of the people we've served ads to in the last 2 weeks or last month, and build a big logistic regression model. And what this will do is learn a weight for each binary feature that we have here. So it will learn a weight for each of the campaigns, and it will learn a weight for men in general and women in general. What does this model learn? Well, it says that campaign A is more popular for everybody than campaign B, and it may say that men are more likely to click on any ad than women. But what it's not doing is allowing us to discriminate between a particular campaign and a particular person type. So that could give us something, but it's not going to allow us to target individual campaigns. So here's another simple mechanism. We can solve that problem. We can build one model for each campaign. So now we learn exactly what type of people go to campaign A and what type of people go to campaign B. So many years ago, I tried this approach, built a system, worked quite well. But there are a couple of problems here, and particularly with mobile and targeting, is that there are many, many different campaigns. So you're going to build many models, and that means your data is spread very thinly, and it's going to take a long time before you can get sufficient data for a new campaign to work on. And there's a few other problems. Learning is transferred from one campaign to a new campaign because each model is independent, and there's no the common learning is learned several times. So this sort of approach can work for a small number of campaigns, but not a large number. So we can go a little bit further. We can build a single model, but have interaction features between the campaign and other variables. So now, with interaction features, we're creating a new bunch of features, which is the campaign name and whether the person was a male, the campaign name and whether the person was female. So now with this larger model, then you can learn all the common learning just once efficiently. There's no redundancy there. And we can also learn that a campaign appeals to men and a different campaign appeals to women. So that's fine. That works quite well. And I in fact implemented a system like this for a previous company using reinforcement learning, doing real-time learning using reinforcement learning, doing exactly this. So all of the interaction variables explicitly, and it to the pot, put it into the reinforcement learning engine, and the system learns quite well, but we still had problems that there was much learning lost when a campaign was terminated. So when a campaign disappears, then we lose all the learning for that type of campaign. So what we then went on to do was to create features of the campaigns themselves. So if we've got two similar campaigns, then like tennis rackets and tennis balls, these are both sporting goods. We can create interaction features that are based on sporting goods, and some learning is transferred. So we can do that. And I should say, just before we move on to that, I've also done this, and it's worked quite well. One of the problems here is that as soon as we create interaction features on many different attributes of a campaign, so we start to get this huge number. And in our previous reinforcement learning engine, we easily got, more than 1 million features. And that's not a problem per se. You want to be able to execute quickly, but still 1 million is a big number. And we also have problems with noise as well. So in 1 million features, you're going to get a lot of random noise. So we had a system that worked well, but there were still problems. So where do we get to with LoopMe? So we've sort of come round, and where we are now with LoopMe is that we're using factorization machines. Factorization machines give us, answer a lot of the problems that I've mentioned before, that I've had over the years. So factorization machines are, at the core there's logistic regression, but we are learning the bias and one-way interactions. They're the normal feature interactions you would have with logistic regression, but automatically, without us directly creating complex interaction features, then the factorization machines are giving us all of these two-way interactions, but crucially, these are going to be factorized down. So instead of us getting 1 million features, we have a mechanism, and 1 million weights in our model, we have a mechanism to reduce this to a reasonable number. So, there are problems, of course, with factorization machines, but we now have all of the interactions between campaign features, and all other variables, and the result is a manageable model size. So here's a comparison of factorization machines and the variable Wabbit implementation that we also had. So this performance measure, I created this slide for a more business orientated audience than this, and so I sort of dumbed down. I think this is normalized log loss, but I had to change it from the technical name to something like performance. But the key thing is that on this example, we were running this from beginning of June up until, this is 3 weeks in June, and we're looking at the performance of the variable Wabbit model, which is in orange at the bottom, and we're comparing that to how the factorization machine worked at that same time. And the fact that we model easily all of those interactions, the fact that we managed to compress or factorize the result gave us a clear and consistent increase in performance. So, what we would typically do here is, is when we have a new idea, we would try it out. These results come from substituting the new factorization machines behind our then existing variable Wabbit scoring mechanism and comparing the results of the two predictions. So run that for a period of time, evaluate how the new system does. If it's good enough, we can implement it. If it's not, we can either dump it or improve it. Okay, so that was the that was the model building. So at this stage, in our shiny new factorization machines, we've got the good predictions, and we need to put these into our bidding algorithms. So there's, I'm not going to say a lot about our bidding algorithms because we've got a lot of work which is still underway, and I just want to sort of give you an overview of what some of the problems are here. So when we're bidding, then ad exchanges run a second price auction. And so if you think about a second price auction, you go onto eBay, all of the books say, with a second price auction, the incentive is always to give your best bid straight away. Now eBay is slightly different because we've got time. Here we've got a short period of time, so the idea is that every DSP will bid their maximum amount. However, if you do bid your maximum amount, then you can do this simple calculation. So if you've calculated the probability somebody's going to click, and the CPC, the amount of money that you're going to get from the advertiser for a click, then your expected return, and you can bid this amount or less. So that's very straightforward, except life isn't that simple. An advertiser will always specify a total budget, and there will be a campaign lifetime as well, and mean that this simple strategy is not optimal. There's a lot of research being done on real-time bidders, and we have done a reasonable amount of work to get bidders working. So what I'm not going to do at this stage is tell you a lot about it, except to say that this is a sort of ongoing research area for us. We can see that here's just some typical examples of bidding strategies that we've tried, and I think this is CPM. So essentially, CPM of $3, we can reduce it down with a good bidding strategy to a CPM of 1.4 or something, which is a very big improvement. Right. So we've talked about data, we've talked about model building, we've talked about bidding very briefly. I wanted to talk a little bit about future research areas for us. We have a lot of interesting problems to solve, and this might give you some idea. So, the first thing we're currently working on is a slightly digital fingerprinting. So, we identify people with a device ID, but mobile web, for example, uses cookies, and they use non-persistent cookies. So it's very difficult for us, if anybody's using mobile web, for us to be able to identify them, because their cookie ID is going to change at the end of it's session to session, so it will change when the app is restarted. So, we need to think about better ways that we can join up individuals, and currently most mechanisms are very poor. Another big area is about changing behaviour. So, what we really want to do is to target the ads at people that will respond to that in a positive way. So we don't just want to send the ads to people who would have clicked on it anyway. We don't want to send the ads to people who never click on anything. We want to send it to the people who will get a new piece of information from seeing that ad. Okay? We want to make advertising useful. We all know the situation where we're bombarded by ads and we're just not interested. But, you know, sometimes people interact with that ad because they found it useful. And what we need to do is identify those individuals. So it's not about targeting to the people who would click anyway. It's about targeting to the people who have learned something from that ad itself. Next one is low frequency events, and you know I've done a bit of work with this over the years, and you know the ad targeting industry is a little bit behind the times in this area. So a lot of ad targeting is still on the basis of clicks and install. But when you speak to advertisers, they don't really care if you click on it. When you speak to companies, they don't care if you install the app. What they want is for you to buy a product or to use the application. Those things are much more important than just clicking or just installing. And so, increasingly, people are asking for, you know, people taking actions, people buying product, or people buying product, or people using an application. Now, by definition, people buy fewer products than they click on. People use fewer applications than they install. I've got loads of applications on my phone that I thought was a good idea and I never used it. So this is a much harder problem because these events are very low frequency. There's a whole load of issues about how you optimise on those really low frequency events. I'll sort of skip over this. It's about changing behaviour, but it just puts a little bit more meat on the bones. So let's talk a little bit about lessons learned. You know, so some of these things are obvious. Some of these things are obvious with hindsight. Some of these things we sort of struggle with for years with a suboptimal approach. But so firstly, this is always having a control group to be able to measure your performance against a non-targeted group is extremely important. But it's not important just to have a control group, it's important to do it right. It's worth putting the effort in. So, you know, typically for us, the first time we see a visitor, we randomly assign it to a customer group. And typically, you know, that would be 90-10, something like that. So now we've got 2 concurrent groups, and this will give the most accurate possible estimate of performance of our algorithms. Now, it sort of sounds obvious with hindsight, but without it, then we're really, you know, stumbling around in the dark. So it's important to get a system like this working. It's important to get it completely perfect. Second thing, measure everything. So this is just a messy old picture of our day-to-day performance of our model building algorithms. Looks like a bit of a mess, a few milestones in there as well. But this is one of maybe 100 different views we have of the system at any one time. Extremely important to, you know, to produce views of everything. Without that, then it becomes very difficult to see exactly what's going on. Next thing, learn this lesson the hard way, visualization. So it's not a very good quality picture here, but improved visualization of what the model is doing, what your machine learning is learning, what people look like is highly important. Customers always ask, you know, what has the system learned? And I can sit down with them and tell them in great detail about weights and all this sort of stuff, and they're just not interested. What they really want, they want these nuggets of information. But, you know, the people who click on the Volkswagen brand campaign predominantly, you know, live in the north of England and have an income of X. That's the sort of thing we're looking for. And providing that information really goes a long way to giving sales something that they can give to customers, giving marketing something that they can sell, and also communicating to the rest of the business that you're actually doing something worthwhile. Okay, so this was the summary of the lessons learned. There's a couple of other things on there as well. So we talked about the control group, measuring everything, visualization of results. A couple of other things I'd say as well. One is investigate every issue. So learning systems are very, very tough to debug. It's very hard to know when a system is learning everything it should learn. And you know, it's very difficult to get a good set of unit tests that will satisfy that. And over the years, you know, many times these sort of small discrepancies that don't look very serious appear in the dashboard pages or the status pages on our measurement pages. And it's only on closer examination do you find something in there that, you know, is potentially serious. So if in doubt, spend the extra time, go back and have a look. There's always too many bugs for comfort working under the hood. Next thing, don't rely only on high-level metrics like log loss or area under the curve. It's easy to get fixated with, you know, evaluating something with your standard metric, and everybody's happy because the overall log loss comes down some fractional amount, you've made some fractional improvement, but you sort of have to go back and look at both the detail, the big picture as well. What are we actually learning? You know, you can miss out things like how well your interactions are working by concentrating purely on the area under the curve or log loss. So that is it. So, thank you very much.
Thank you for the presentation. We have time now for only one question. Anybody want to ask?
Thank you for your presentation. Maybe I missed something, but do you use some text analyzing for searching your users in public posts or comments in social media?
Sorry, could you repeat that? Sorry, the question was?
Do you use some text analyzing for searching your users in social media, like public posts or comments on some videos or posts?
So we have to be very careful about collecting data which doesn't have the consent of the users. And going into social media is a bit of a minefield. So our, you know, I would love to be able to do that, but it's a little bit close to a sort of big brother approach of collecting too much information. It, you know, as a company, we can only collect the data which we have full buy-in and consent for. So I'd love to, but we try and distance ourselves. It's all right for Facebook. It's not
One more question.
On one slide, we can see your competence and history. And the question, how do you solve the problem called start and data age? For example, yesterday I was in London and now I'm in Krakow. How long time I don't see advertising for London?
How long time?
I'm seeing information about London.
So how would we see the information about it?
I mean, advertising and another information which corresponding with my location. If on one slide you show that you use location for information from it, how long time you will see if I change my location?
Oh, I see. So we have various limits on how long we can store data. The RTB exchange will generally put limits on how long we can keep data for. It might be 6 weeks, it might be 6 months. But what we would do is not, is look at the most recent data and weight our segments on that most recent data. So you may have 3 or 4 data points in the Ukraine, and 1 in London, and then 1 back in the Ukraine. Well, that tells us that that was probably a visit to London, rather than that's what we were. So it's about using that information intelligently.
Thank you for a very interesting presentation, and now we have a little break.